Hey, what's up, guys? And welcome to math class. Today we are learning about transformations.
Keep going. This is great.
Use the rules as before. No more.
When you're laughing so hard, it doesn't audibly come up very well. So, yeah. Anyway. I think what Kara was attempting to say was that, yes, we are going to jump back into the transformations. Now, I think that this is something that can be very quick, hopefully painless, because we're not changing anything. Just because we have an exponential function doesn't mean that we have new transformational rules or anything like that. The same transformation rules that we studied back in Chapter 1 with parent functions, same ones that you used all throughout Algebra 2 last year, some of which you used back in geometry. Again, hopefully we're getting to the point to where we just understand that if we have a graph and we notice this happens in the equation, graphically we do that. If this happens, then we do that. If this happens, we do that. So just, again, little template here. We could go through all of that. I think that it just makes a little bit more sense to actually see it. So where we're going to start here is with, again, I'm assuming the one that the parent function that we feel most confident, comfortable with is the quadratic. So if we have f of x is equal to x squared, how is that going to change if we have x minus 3 quantity squared? We're going to shift to the right 3 units, aren't we? Okay. What happens if I add x squared minus 5? Notice that we're subtracting in a different spot. Now we're vertically, we're going to move down 5. Okay, what about if I have that coefficient of 3 up front? Vertically, we're going to stretch that thing 3 times. Good. Now, what happens if we jump over to the exponential? Same as we used on a couple slides ago. What if we're using this as our basic? I don't want to call it a parent function, but I'm going to say parent function here. Again, it's the parent function so long as the base is 2, I guess. But if this is where we're at, no adjustments, we haven't shifted, we haven't done anything else. This is the most basic, option, I suppose, anytime we have a base 2 exponential. What are we expecting is going to happen if I have 2 raised to the x minus 3? Right. The subtraction is occurring within the function, so yeah, we would expect to move to the right 3, just like we did with the quadratic before. What if we have 2 raised to the x minus 5? Shifted down 5, good. All right, now here's the next one that we have to really be careful of. Okay, we've got to be careful with this. What about 2 to the negative x? It is a reflection, but I was going to say, a lot of us, we've gotten so used to anytime we had a reflection, we were always reflecting over the x-axis. This one is not being reflected over the x-axis. Again, when we had the quadratics and the cubics and the square root functions, if we had reflections, we pretty much were always reflecting over the x-axis. Now that we have the exponential, we are rarely going to reflect over the x-axis. Instead, we're going to reflect over the y-axis like this. Okay? Again, hopefully mentally you've already gone there, but anytime we talk about exponential growth, immediately we should be probably factoring in or thinking about exponential decay. It's just a matter of which are we growing or are we decreasing? How's that going to work? Okay? Can we do combinations? I suppose. Can we have 2 to the negative x minus 4? So we already know that we're reflecting in the y-axis, and then the minus 4 implies we do what? Then we're going to shift it down 4. So we would go directly from the parent to there. All right, so guys, more than anything else, what we're trying to get at with these little examples, hopefully you're believing us. I don't know who us is. You're believing me when I tell you that it's the exact same, the same transformations. So when it comes to graphing these, we're going to talk about it a lot more throughout Chapter 3. But basically, we know that we're going to hit the point 0, 1. Then we know that we're going to have our secondary point, which is over 1 up the base. As long as we have those 2 points, generally that's enough. We could always find more points using t-charts, creating t-charts, but once we have that parent, then we're going to transform. We're going to shift and move things around. All right? But there's just a couple of examples. The copy didn't come out looking great, so again, we had a better example on the slide. All right, so one of the things you're going to be asked to do on your homework assignment tonight, very simple. It's not even asking you to graph them. It's just asking you to describe the transformation. So if our base unit here, our base function is f of x equals 4 to the x, what are we doing 4 to the x minus 2? What's happening there? Up, down, right, left, how much? What do you think? We're going to move right 2. Good. What about this one? 4 to the negative x plus 3. So the negative x means that we're going to reflect All right, so guys, hopefully everybody hears me. If you just write reflection, you understand that that's not correct, right? We have to imply. We have to denote which axis you're reflecting over. And then what about the plus 3? What does that do? That's what it is? Wow. Okay. All right, so next up, this is more of an application. Well, I guess where we're going eventually is more of an application. But please understand that as we're talking about exponential functions, very, very soon we're going to be getting into logarithms. And once we're into logarithms, the natural logarithm is good. Then you'll like chapter 3. But again, the natural logarithm is going to come up. So when we're talking about the natural base, E, E is approximately 2.718281. Please don't ever type that in as 2.71. There's a button on your calculator for E. That's the precise. This is a rounded approximation that'll get you close, but we want to be as exact as possible whenever we can. So we're going to use the E button on the calculator. So if you're not certain where that's located, I can try to help you out with that. But again, we want to make sure that we're aware that E is not a variable. E is a number. Okay. Anytime we have E within a formula, that's not an unknown. Like I said, it's not a variable. We know exactly what E is. It's a button on the calculator. We can clean that up. Okay, so E is going to be that natural base. Once again, f of x equals e to the x. That's what we refer to as the natural exponential function. E is an irrational number, so be careful with that. Cannot be written as an exact amount other than just E. That's it. All right, so like I was saying, that we have some applications here with E. There are many applications coming here in Chapter 3. We're starting out here in Section 3.1 with the absolute most basic, simplest interest type problems. Now, some of the numbers are going to be a little bit more complex, but as far as the formulas are concerned, I would imagine that you probably initially saw these formulas in pre-algebra, maybe even the class before that. Okay, when you were in maybe 6th or 7th grade and you were first starting to work with exponents and how they worked with the calculator, these were like the go-to problems as far as how things worked. And again, and they're great, and frankly, that's part of why we're doing what we're doing in here as well. But obviously, when you were in 6th or 7th grade, almost everything was given to you and it was provided. So again, we're taking a lot of the training wheels off and doing more word problems. So the two different types of compound interest formulas that we have the first here, A is equal to P times 1 plus R over N raised to the NT power. This is what we're going to be using if you're compounding interest non-continuously, so a certain number of times per year. Maybe you compound the interest 1 time per year, then N equals 1. Maybe you're doing it quarterly, so N would equal 4. Monthly, N would be 12, or daily, 365. But this, again, is one of our options. It's the way that some of the interest is going to be calculated. Another way, though, is the continuous, and that's where E comes in. More, effectively referred to, or commonly, is a better way to say this, as the PERT formula, principal times E raised to the RT power. So with both of these formulas, A represents the total amount, P represents the principal. Principal is the original amount. So what did you put in to the account, or what did you start with in terms of value? Your original deposit, whatever. R is going to be your rate. Now this is the most common spot where people make mistakes. If you're told that the rate is 5%, you don't put a 5 in place for R. That's a percentage, so we have to think decimal. 5% would be like 0.05. Okay? N, like I said, that's going to be the amount of times that you're compounding per year. So if it were quarterly, 4 times per year. Monthly, 12 times per year, like I said a minute ago. Okay? You'll notice that N value doesn't show up in our second formula because you're not compounding it any number of times per year, you're compounding it continuously. And then T is always going to be measured in years. Some of the problems are going to be a little tricky. Intentionally, they're going to tell you, yeah, you're doing this over a 6-month period. They're trying to bait you into putting a 6 in place for T. If it says over 6 months, how many years is that? It's half a year, right? So you'd have to put in 1/2 or 0.5 for T. Yeah, you're probably going to want to know these. We'll talk about it a little bit more, especially the PERT formula. I may give that one if you ever needed it, but Yeah, I don't know. I would say let's start to try to utilize it enough to where we can remember some things. All right, let's go ahead and practice this first one. It says that a total of $12,000 is invested at an annual interest rate of 9%. Find the balance after 5 years if it is compounded quarterly. So by telling us quarterly, what is that saying?
4.
What is 4 though? I don't know what you mean by that. You're just saying numbers right now. N is 4. And that's what that means. N is 4. Now the rest of this, hopefully we can fill in. The amount, that's what we're trying to find. We don't know the amount. What's the principal? What are we starting with? $12,000. We just said it's compounded quarterly, so N is 4. The rate, we said 9%. So is that 9? Just write a 9 down. 0.09. And then T, how many years is this happening? It's over 5 years. So once we have this information, now we can plug into that formula. So A was equal to P times 1 plus, what was the rest? R over N times N T power. Good. So at this point, it's a big giant substitution problem is really all that we have. So we don't know the amount. We do know the principal is $12,000 times 1 plus. We know that the rate was 0.09 over N, we claimed was 4, times N, or I'm sorry, raised to the N times T. N is still 4 times T is 5 years. Okay. Questions with how we set that up? Now, guys, I know that a number of you are the type of student that just want to type everything into the calculator and press equals one time. I was going to say, you make my heart hurt when you do that, but I will say that it's possible. Again, don't get me wrong, it is possible, but a lot of us need to know how our calculator operates, okay? Some of us are going to have calculators that are a little touchy, and it doesn't like it when you do that. I don't want you to miss problems that you should get right because your calculator didn't do the order of operations or something like that. So if you were doing this the more traditional way, we're talking 12,000 times, within the parentheses, I probably showed some work here. I'm getting 1.0225 raised to the 4 times 5 is 20. Now, if we're here, if we're doing this, like I said, more traditionally, because we're in pre-calc, does that mean that we get to forget about order of operations? I would say they're even more important now. The most common mistake is that people try to multiply these and then raise it to the 20th power. Exponents first or multiplication. So as we clean this up, I would encourage all of you to check with your calculators right now. Are we all getting $18,726.11 for compounding quarterly? Did we all get that? Ian, question?
Oh, yeah. I told him he thought that.
You mean multiply by 4?
No.
Oh, you left it as just 0.09? Gotcha. All right, so question. Should we expect the same answer if we're compounding monthly or daily or continuously? Should we get the same answer? No, but are we going to get roughly the same? Like, we shouldn't expect that if we compound continuously that we're gonna have like $75,000 or something like that. That would be way too far off, right? We're going to be in the same ballpark, but it's not going to. We shouldn't expect to be the exact same. So continuously, talking the PERT formula now, A is equal to P times E to the RT power. And we already have the variables present. We still are looking for the area, 12,000 times E. The rate is still 9%, so 0.09 times T, which is still 5. So as we type this into our calculator, or if you're doing this separately, what are we getting this time? 18,000 what? $119.75. So it looks like in this particular case, if we use the PERT formula, our account grew more. Again, we had like close to $100 more. Is that always going to be the case? Is continuous interest always going to garner more? Not necessarily. It all depends on the numbers and the time and everything. Each problem is different. I wish that we could say that, yes, this way is always more, this way is always, but it doesn't work like that. All right? So I think that we get it without doing this. The goals, do you want to see your test real fast? Okay, 1 second. The goals here, how did we do? We feel like we know generally how to graph an exponential?
Yep.
Okay? Understand that one-to-one property?
Yep.
We've already talked